Hi there, welcome back to the channel. Welcome to a new project. This time I'm building a inverse RIAA equalization board. If you don't know what that is, I'm going to give you some references and allow you to do what I've just done, which is go down a huge rabbit hole where there is a lot of reference material, a lot of reading to do. But in simple terms, it's a little board that allows you to feed a signal, an audio signal in, a test signal in from your signal generator, and plug it into the phono inputs of any amplifier. Now, why do you need this? Well, again, there's the rabbit hole I mentioned. Just about all amplifiers will have a phono input, and the level that that phono input expects to receive is way, way, way lower than the normal line inputs for your auxiliary, your CD player, your tuner, whatever it is. And because the record industry created a method of achieving optimum reproduction of audio signals on a vinyl record, and they're very low level, and because there are enormous number of constraints regarding how long the groove is, how wide it can be, it's preconditioned, or let's say it is tuned to a particular frequency curve, which the preamplifier stage of any amplifier, the phono preamplifier stage of any amplifier, will put back to a line level signal, which should be flat across the entire audio band. Now, recently, I had an amplifier that I needed to test, and I was able to test all the other inputs. The actual phono inputs were difficult to test with just my signal generator. My signal generator is 50 ohm output. It just puts out a signal at any frequency I want, but it has a flat frequency response. So I can test it at, say, 1 kilohertz, but I don't know how it's going to behave at 100 hertz or 10 kilohertz. So what you need to do, and this is where the research comes in, is you need to pass the signal generator signal through here, out here, to the preamp input of the amplifier, the phono preamp input of the amplifier. And what this does is it sort of preconditions the input signal to emulate the frequency response that a record player would produce. I'm not going to go into all the theory, but there is a lot of theory, and it's very, very interesting to read, which is why I certainly encourage you to check out these sources. Now, probably one of the best articles that you can start with is this one here. It's called the High Accuracy Inverse RIAA Network by Stanley Lipschitz and Walt Jung. This is the, well, I won't say the original article, but this is probably one of the ones that is most referred to in all the material that you'll get. It's from the Audio Amateur magazine, January 1980. And it really gives us a bit of a history of how this network has developed. This is the original, they give it to us as the original Reg Williamson circuit and some modifications. And you can see some optimized values here like 883.3 kilo ohms, and they use 910. It'll tell you why this is not as good as it can be, and the objective of these two gentlemen was to perfect it. And what they've done is they've basically created an alternative circuit, a modification of the Williamson circuit for better accuracy. And you will notice right away that this is purely a passive circuit. There is no power here. This is just resistors and capacitors, which makes it incredibly easy to reproduce so that you don't have to worry about having to use a battery or power supply. Now, obviously, the accuracy or the precision of the resistors have improved through time. So a lot better can be done than what they did. Now here we've got another situation, for example, with an alternative. They also give us two levels of attenuation. You see here you've got one level of attenuation, which is minus 44 dB at 1 kilohertz. Remember, this whole point of the circuit is that it's frequency dependent. So how much level you'll get, how much attenuation you'll get, will depend on the frequency that you're measuring at. So this will give you one output. What they've done here is they've got the same situation with 1 kilohertz attenuation at 44 dB at that output, and there's a second output there, which is 74 dB of attenuation. And the reason for this is that you've got moving coil and moving magnet pickups normally. And because it depends on what input at your amplifier you're using, or rather what selection you're testing on your amplifier, if you put it to moving magnet and you feed in a moving coil signal, you'll get a very low result. If you do it the other way around, it'll go boom, not explode, but it'll probably clip, because the moving magnet levels are about 0.15 to about 0.5 millivolts, and the moving magnet, did I say that right? Moving coil 0.15 to 0.5, and moving magnets about 1.5 to about 3.5. So you can see there's quite a difference there. Therefore, you need different levels of attenuation. And usually, what you'll do with this particular circuit is have a selector switch, okay? Now, if we carry on down, they give us the actual attenuation values for different frequencies, starting at 10 hertz. If you feed a 1 kilohertz signal into a phono preamp at the right amplitude, you should get no difference. You should get zero attenuation. What goes in should go through. However, the minute you start changing frequencies, whether you go lower or whether you go higher, you start getting that change. And you can see that on this curve. Now, when they do it this way, what they've done is they've started using more accurate resistors. For example, 883 rather than the one we saw here, 910. So they're getting closer to the inaccuracy. They're also compensating for the possibility of different source impedances. So depending on what you're feeding this with, you would be able to compensate that as well. The rest of the article will give you a lot of explanation as to how the Young prototype worked and what the alterations were that were made. But I found one article which actually improves on this. Let's have a look at that. And remember, I'll have links to these articles in the description below. I found this article, which is very, very interesting, because what they describe this as is an accurate inverse RIAA network. So this is November 2016, Andrew C. Russell from Ovation High Fidelity. Again, I'll have a link to this below. And what they go into is they're trying to create a reference system. So they are trying to be incredibly, incredibly accurate. In terms of specifications, this is what they give us. Conformity 20 hertz to 20 kilohertz. 0.5 tolerance components, 0.5% tolerance components. Typically, you get 0.025% accuracy. They're also talking about using a 50 ohm output impedance signal generator, which is exactly what I have. So this really interested me. Then they're telling us about the output impedance for the moving magnet and a moving coil. The maximum input 10 volt peak to peak, okay, that's, you shouldn't be feeding this with 10 volts anyway from your signal generator. Normally you'd feed it with about 2 volts peak to peak. And here's what they're giving us. 44 dB for moving magnet, because that's the highest signal that the preamp expects. And minus 68 dB for the moving coil. This is that switchable option at the bottom, and they go and show us the prototype. And then they also go into a little bit of the history that the Elliott Sound Products site gave us as well, showing us the original Williamson circuit and how that was improved. And then they go into their version. They're playing with component tolerances. And there's a characteristic of component tolerances which is very, very interesting. And that is that the more components you use to make up the desired component value, the better accuracy you'll get. And I've seen this before, I can't remember where, but they repeat it here. It improves by √2 for every doubling of the components used. So here's an example. If two 1% 100 picofarad capacitors are in parallel, create a 200 picofarad capacitor, the probable tolerance will be 0.707. So √2 of 1%. If you double that again, you get √2 of 0.707. So you can get incredibly accurate with these values. There we are. If I place 4 in parallel, the tolerance is about 0.5%. 10 in parallel, 0.3%. Obviously, you're getting diminishing returns. But the fact is that you can use multiple components to make up one component, desired component value, and really improve on the accuracy. Now, is this useful for me? Absolutely not. I don't want to create a lab accuracy component or system. I'm looking at something that I can use practically in the very, very few amplifiers that I work on. And I only work on amplifiers when I feel like it, when it's something that I find interesting. I've done the Pioneer. I really enjoyed that. And I've done the Scott because it was so dirty I had to wash it in the bathtub. I really enjoyed that. But I'm not an amplifier person. And quite frankly, I don't particularly enjoy working on amplifiers as a rule. But as I said, there are exceptions. And it's good to have a little tool that you can use. Now, well, look what they've done. You see this whole network over here, right? They've made up that resistor by 6, by using 6. Now look at this. You see that? That's that resistor, 883.3K. They've used 220, 220, 220, 220. That's 880. And 3, 883. They've got 883 kilo ohms made up of 6 resistors. They could have used another 330 ohms in there, but that would really be splitting hairs. That capacitor there, if we look up here, it's 3.6 nanofarads. Look what they've used. 1.8 in parallel with 1.8, in parallel with 1.8, in parallel with 1.8. What does that give you? That gives you 7.2 because you add the capacitances. Bloody hell. Now you put double that and you halve it again. So they've got 3.6 nanofarads made up of 1, 2, 3, 4, 5, 6, 7, 8. So the accuracy of this capacitor, if you measure from there to there with these 8 capacitors by themselves, you should get very, very, very close to 3.6 nanofarads, which is what they were trying to achieve here. And they've done it brilliantly. Now if you go down here, you've got the same situation. We've got that 75 kilo ohm and 1 nanofarad, okay? So 75 kilo ohm, what have they done? They've got 150, 150, 150, 150. That's divided by 4, so that is 75, 37.5 kilo ohms. And then they've got another set that makes up 37.5 kilo ohms. Put them in series, you get 75 kilo ohms. But you have doubled. So you've improved the accuracy, the percentage accuracy of those values tremendously. This is even crazier. Here you're trying to get 1 nanofarad. And they've gone 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 by 100 picofarads comes to 1 nanofarad. Perfectly logical. The part that really interested me was this down here. I've really copied these values from them. They've got 560, 560, 560, 560. Those two halve, the 2 in series double. So this is a 560 ohm that's going to go out to one of the outputs, moving magnet. And then they've got 2 82s in parallel, which make 41 ohms in parallel for the moving coil. That's it. That really is it. So if you have a switch over here, you can select between that output or that output. And they go into the accuracy, and it's amazing. I mean, they've got this particular site, you can look at that. They've got all the descriptions here. They've got the test set up. They do a square wave testing. They basically give you the whole business on how to build it, test it. And they've even got a PC board layout that you can use. All components 0.5% or better. So they've even gone to the extreme of using 0.5% components, and then you're doubling up and improving by root 2. There we go. This is a very, very important reference, which again, I will link below. Now, all this is great, but the level of accuracy they're talking about here is way beyond my needs. Let me show you what I did. This is really all I needed. 1 channel, 2nd channel, right, for stereo. Now, what have I done here? Well, remember that 883.3? This is me, 660, 880, 883.3. Well, I've actually got a little bit better than the highly accurate one in terms of value because it's 3.3. So 883.3K made up of 1, 2, 3, 4 resistors, 3.6 nanofarad made up of 2 capacitors, and then here 75 made up of 2 resistors, straight 1 nanofarad capacitor. I didn't go into splitting it up or anything like that. The 560, I've used 1 resistor, and then I've got 2 82s in parallel to give me 41 ohms. Now, the values are the same. The values are correct. Now, you can go crazy, and you can make these 0.1% accurate resistors if you want. It's not what I need, so I don't do it. Here's my switch, moving magnet, moving coil switch. It's a double pole, double throw. When you flick it one way, it switches this channel and that channel. When you flick it the other way, it switches, again, both channels to the other point. The lower one being the moving magnet, the moving coil, and the top one being the moving magnet. So that's it. That's all I needed to do. And the board, again, is incredibly simple here. Here's our PC board. The input, I've used a vertical stereo RCA sockets. So they're both in one, makes it easier to then, you'll see it when I build it, makes it easier then to apply. The output is the same. The switch I have not actually put on the board. I've put the connectors for the switch here because I'll tell you what my idea was here and how I changed my mind on that. But basically what I've done is I've reproduced the circuit. You know, it's mirrored from one side to the other. This is the left channel, this is the right channel, or vice versa. At this point, I'm not too worried about that. But that's it. That's the board, and that's the one that I ordered from PCBWay. And that's the one that I have in my grubby little paws right now. So let me show you the actual board and the build and the result. Our board is done. This is where the input sockets go, the output socket. All the rest is mirror image, one of the other, as you can see. I've got, I lay out things as neatly as I can because I like looking at the result. I mean, these things can sometimes look like a rat's nest, and I prefer to make it all nice and neat. The switching is there. You could actually fit a switch, a double pole, double throw switch, like this one, but I've decided to leave it out. You'll see in a second why. The underside, there's nothing, just the through holes. So this has got to be populated and soldered, and I won't bother you with that, so we'll just apply a little bit of magic. 1, 2, and there we go. Done. You see, I chose these particular sockets because I wanted to fit them to the faceplate, a faceplate. Originally, I wanted to build it on one of these, which would be another addition to my undershelf set of tools. However, I've got a bit of a problem. Well, two things really. One is I very rarely use this. Very, very seldom. It is so rare that I don't think it's worthy of being placed at just arm's reach. And the other thing is I've run out of these guys. I've got to get some more cut. And you might think this is strange, but finding a aluminium supplier here that'll cut this for you in Madeira is actually a bit of a problem. I've got one left of the 10 centimeter ones. I've got a few more of the wide ones, but I've got another project in mind that I'm going to need one of these, and that definitely is something that's got to be under the shelf because it'll always be used. So the result is we've got our board built up, and as you can see, there's no power. This is completely passive. Input left, input right, output left, output right, and hopefully all the calculations worked out well, and the result is a signal that is suitably attenuated. Attenuated at, what is it, 44 dB if the switch is in one direction, 44 dB at 1 kilohertz, and then it goes higher below, lower above. So we will have our curve reproduced by this little baby, hopefully. Now, I'm not going to test this in an actual amplifier because right now I don't have one under repair or restoration, but I mean, this thing is so simple. You know, there's not much that can go wrong. Those circuits have been tried and tested for decades, literally. And so perhaps when I have another amplifier that I work on and I want to test this, I'll show you the result. Now, the one thing that this does need, and I don't have that yet, is the metal box, because the signals coming out of this are so small, really small, that they need to be kept away from any noise. The workshop here is full of noise, electric noise, so I need to put this in a metal box. But in the meantime, I found a solution using my 3D printing. And here it is. It's just a very simple box, and it's got the holes here for the input sockets and the holes for the output sockets, a little hole there to screw it in because that does get held fixed to the front. There's that hole in the middle for the switch, and the switch is this guy. I'm just going to finish this up, put it in there, and I'll show you the final result. Okay, here we've got it. The switch can now move anywhere, and I'm not even sure whether it's supposed to be like that or like that. I'll have to check to see which is the higher level, but let me put this in the case. Here we go. I've got this coming from the signal generator. Only one channel is active because I'm only going to measure one side here because my scope, although I've got 4 channels on here, I can't get that on the screen in a way that would make sense. So I'm keeping it as simple as possible. The signal I've got coming in here is 1 kilohertz, and it is 10 volts peak to peak. The reason I'm giving it 10 volts peak to peak is because I want it as high as possible because this thing does a lot of attenuation. In fact, I think 44 dB is like 150 times less. All right, so if you put in 1 volt, you're going to get a very, very small output, and that makes it difficult to read. So we can see it on the screen over there. And if I go flick it down, it gets much smaller. So that is the higher attenuation, right? That is the, what is that? For moving coil. So it's moving coil, moving magnet. Let's leave it on moving magnet for now because it makes it a lot simpler to read. Let us see what happens. I'm not going to do a boat plot or anything like that. I'm just going to see what happens when I increase the frequency. Actually, when I decrease the frequency, because I know it should go down. So we're on 1 kilohertz, 900, 8, 7, or 6, 5, 4, 3, 2, 1, or 100 hertz. So you see, it is working as expected. I'm just going back up, and now I'm going to leave it at 1 kilohertz again. Hang on. 1 kilohertz, I'm going to drop the scope, and I'm going to go up in, let's go up in kilohertz ranges. 1, 2, 3, 4, 5. Whoa, got to drop the scope again. That's 6, 7, 8, 9, 10. So effectively, it just keeps going up. At 20 kilohertz, we are now getting, let's see, we're at 572 millivolts, and at 1 kilohertz, we're at 64. So we're like 9 times more, 10 times more. That's almost 20 dB. I'm not sure if that curve is correct. Quite frankly, I'm not too bothered, because I will be able to test this when I have an actual amplifier with a good phono stage. I'll be able to feed a signal in there, through there, do a full sweep, or do a sweep from 20 hertz to 20 kilohertz, and the result should be a flat line, right? Because this thing is dropping it, the other one, the phono input, is increasing it, or reverse, depending on what frequency you're at, so the result should be a flat line. Now, I know that this is incredibly sparse testing for a project, but I'm confident this works, and I'm not going to waste my time or your time on this. What I will do is I'll give you a link down below to a video that X-Ray Tony published. Now, to me, he is the guru of high-level 80s amplifiers. The guy is amazing, and he did a video precisely on this topic, where he builds a couple of kits that he found. These things are very readily available as kits, and he describes this in lots and lots of detail. Very good description. X-Ray Tony B, go check out this video, linked below, and I'm going to try to remember put it above. And you'll learn a lot more there than you will from me trying to experiment with different boat plots that I don't have the equipment for. And so that's what I'm going to leave you for now. And I'd like to thank PCBWay for the boards and sponsorship of this video. I hope you've enjoyed it. If you have, click like, share, subscribe, and all that jazz. And if you want to support the channel directly, you can do so on Patreon and PayPal. Once again, thanks for watching. Bye for now, and stay safe.